Hello, my name is Dr. Jamie, and I'm going to be talking to you today about true gene diagnostics and our mission, which is to double cancer survival rates. And we hope to be doing that in the next 10 to 15 years. So without further ado, let's get started. So what do we have is we have a better companion diagnostic test for HER2 positive breast cancer patients, right? For the first time ever, right? We can tell you if you are sensitive or resistant to one of the three most common HER2 drugs, right? That's what we do. 90% of all prescriptions for HER2 positive cancer are one of three drugs, and we can tell you whether or not you're sensitive or resistant to those three drugs. No one else on the planet can tell you if you are sensitive to those drugs or not. They can sometimes tell you if you're resistant. That's it. Now, what that means is that if you're resistant, it means the drug is for sure not going to work. It's just generally accepted that if the drug doesn't bind, which means resistance, it means that the drug is not going to work, right? And if the drug binds, which means sensitive, right, the odds of that drug working, according to studies, are about 80% chance it's actually going to work if it actually binds. So that's what it is that we're able to do. We're able to tell you whether or not the drug is actually going to bind. Now, why is that a problem? Why is that an issue? Well, this is something almost no doctor ever tells you, is that a large percentage of drugs will not work on a certain percentage of people, and nobody generally knows which people those are. So for example, if you've got depression and you take an antidepressant, 38% of the time it just won't work for you. Nobody knows which 38% of the people it won't work for, but it just doesn't. Right now, sometimes they maybe know 1 or 2 or 5% of those, percentage that it doesn't work for through genetic testing, but mostly it's mostly none, right? And then there's a whole range, and all the drugs have this, right? And it ranges anywhere from 38% with antidepressants all the way up to 75% of the people who take a cancer drug, it will not work for them. And nobody knows which 75% of those people are in general, right? Again, there's always exceptions and small percentages, but just as a general rule of thumb, most of these people, we have no idea whether or not the drugs are going to work for them and which ones they will and won't work for. And it's just a statistical average. Now, what does that mean? If 75% of the time that you're resistant to a drug and it doesn't work for you, well, what that means is that there's a 75% chance any cancer drug you take is not going to work for you. And you'll take it for 6 months before they evaluate whether or not that cancer drug is working for you. And if that cancer drug is not working for you after 6 months, guess what they're going to do? They're going to change to another drug. And guess what? Statistically speaking, there's a 75% chance that drug won't work either. Now, it's actually a little bit lower statistically because two drugs not working is a smaller percentage chance, whatever, blah, blah, right? But you start to get the idea. So now 12 months later, if you're still not dead, right, if you're still alive, what will they do? They'll try another drug if you've become resistant to that cancer drug. So 18 months later, you've tried 3 different drugs and hopefully one of them has worked. And if not, guess what they'll do? They'll try yet another cancer drug, right? Because they just don't know which ones people are sensitive to. Nobody on the planet knows that about any drug until now. And now you start to see, why are cancer survival rates so horrible? Why are people so scared about cancer? This is why. Of all the drugs out there, nobody knows which ones you're actually sensitive to or not. So who is it that invented this technology that allowed us to predict this? So I'm going to share a little bit with you about Dr. Martin Schiller's story, because I think it's really relevant to how this came about. So he got the choice to teach any class he wanted at UNLV. And what he decided was, I want to teach the 25 greatest scientific discoveries of the last 500 years. Well, he couldn't find anyone else teaching that class, so he literally invented the curriculum for that class. And one day after class, one of the students came up and said, "Hey, Dr. Schiller, what would it take to be one of the next 25 greatest discoveries of the next 500 years?" And well, they started talking for a bunch of hours. And one of the things they thought about was, well, what do all of these discoveries have in common? Because Dr. Schiller never thought about it before. And over half of them were better ways to measure something, right? So for example, when they invented the microscope, right, better way to measure something, they realized, oh my gosh, it's not evil spirits killing people, it's these little things, bacteria, that we can now see. Wow, changed medicine forever, right? As one of the examples. When they discovered a better way to measure the cells, and they're actually able to stain the cells and see that, oh my gosh, there's these things called genes in the cell that are driving the functions of the cell, changed medicine forever, right? So 12 out of those 25 were better ways to simply measure something. Now, Dr. Schiller at this point in his life had been working with genetics for 20 years, and he realized, you know what? There is a large percentage of people who are, sorry, large percentage of genetic mutations, 99% to be exact on average, that we don't know what they do in the body. So what if there was a better way to measure these genetic mutations and their functional effect on the body? Would that help us better understand a lot more stuff? And that's when he had the idea. He locked himself in the room for 4 days. He came out with whiteboards full of notes, computers full of notes, handwritten notes, which is now the predecessor for what's called the Giga assay. Now, what the Giga assay does is it produces more quantity of data more accurately by 100-fold than any other assay on the planet. Now, if you don't know, what is an assay? An assay is just a fancy word for a way to measure something. So we called it the Giga assay, right? Computers, Giga, right? Giga assay measures 100 times more data more accurately than any other assay on the planet. So it's a huge leap forward. Now, just to give you an idea, 75 published papers. Now, how many people on the planet have more than 75 published papers, right? Not that many, right? Literally thousands only. Most scientists are lucky if they get 1 or 2 published papers in their life. And Dr. Schiller actually already has 4 published papers on this Giga assay and related technology that derives the information that leads to our HER2 positive test telling you which drugs you are sensitive to or resistant to, right? So this gives you the scope and magnitude of how smart Dr. Schiller is and what his work has actually been able to do throughout the course of his lifetime, right? It puts him in the top 1% of scientists in the world in reference to published papers and the amount of work that he's done and what it's changed. So now let's look at, what have we been doing for the last 10 to 50 years? Well, 50 years ago, people started doing experiments in tissues and seeing how did the tissue respond? How did the tissue react, right? 10 or 15 years ago now, they started doing groups of cells, right? And they would signal average. They take the average of all those cells and see what the response was, right? And so like 10, 15 years ago, people started creating mutations, right? Genetic mutations, one specific mutation. They put a bunch of those, thousands of those cells into the same petri dish, and then they measure what happened to the average function of that cell based on those one mutations that's in every one of those cells. And that's what we've been doing, right, for 15 years. So now you see why. Why is it that 99% of all genetic mutations are unknown? Because there's an average of 190,000 mutations per gene and literally thousands of genes in our body. And so to measure each one of them, right, and it takes 6 months for every one of them, each one of them that you do, it takes 6 months, right? So to do that, it's taken a long time to do it. That's why there's so little we know about so many mutations in the body and their functional effect. Now, the problem also with this is that what they've been doing for the last 10, 15 years is when you measure one mutation in multiple cells and average what happens to the functional effect, you don't get very good, reliable results. Now, that means that you have to repeat this experiment over and over and over again, 100 times, 200 times before you start getting reliable results. And that's 6 months each time you're doing that experiment. Right? So you'll see that this is why genetics and the information we know about genetic mutations and their functional effect has been slow moving. Now, this is where the Giga assay comes in. This is what Dr. Schiller invented. This is the large assay. Is he's taken it from tissues to individual cells, average to each individual molecule or cell. He can literally barcode an individual cell to tell you which cell it is. He can tell you which mutation that cell has, right? So now he can then measure the functional effect within that individual cell. So now when he puts hundreds of thousands or millions of cells into one experiment, he knows every single one of those cells, what their mutation was, what their functional effect was, and he can read them with this, I don't know, he's got a big fancy cytoscopometer or something, I don't know, right? I don't even know myself, right? But this machine that literally reads each individual cell at a time. It sorts them and it reads them and it sees how much the functional effect of that cell has been impacted. At the same time, it reads which actual mutation was in that cell creating that functional effect. And so what that means is in science, there's something called a p-value. Now, you don't have to worry about those 20 zeros that are sitting there as the average p-value. What's important to understand is this, right? Is that when a scientific study gets a p-value of 0.05, right? Just 0.05. When a scientific study gets an average median p-value of 0.05, everybody's jumping for joy because that's kind of taken as truth to mean that this scientific experiment conclusively proved that this, whatever it is they're proving, worked because we have a median p-value of 0.05. Well, this is way better. 18 zeros better, right? That's how accurate this data is. And not only is it way more accurate, but it can do it with 10 times, 100 times, 1,000 times more data than any other assay out there on the planet at this level of accuracy, right? So that's why he has more. Now, let me put all of this. So if you didn't understand any of that stuff, don't worry about it. I'm going to make one simple statement for you to show you how powerful this giga assay is. Ready? Is that we as in Helogenics has more measured data on the HER2 mutations in the tyrosine kinase region and their functional effect than the rest of the world combined. And they have had a 40-year head start. The rest of the world has 40 years of measuring the functional effect of the mutations in the HER2 gene. And we have more data than the rest of the world combined and its functional effect on the actual cell. That is how different this giga assay is. And that's why the test that we provide you with this data is way more powerful than any of those other tests out there, right? So it's just night and day difference, literally. Actually, I wouldn't even say night and day. I would say solar system and galaxy difference, right? Like it's just out of this world different, right? So what you're looking at right here is a visual map, right? And all these little squares represent one of your amino acids and a possible mutation. The black square represents what your genes should be, right? And every other square represents a possible mutation of an amino acid in your gene, right? So now, what you're looking at is something that no one else on the planet has ever seen before, unless they've seen one of Helogenics or our presentation, because nobody else on the planet has this data, has all of this data, I should say, right? On average, right now, what this represents here is each one of these lines up and down represents one amino acid, right? And these across the sideways here, these represent the possible mutations of the amino acids, right? And so actually, technically, this little picture you see here goes off to the right of the screen by like 3 or 5 feet, depending on the gene on average. But this is just one little snippet to fit on a PowerPoint slide to give you an example, right? So on average, humanity knows about 1% of these squares for each of the genes. Some genes like HER2, we know about 10%. Other genes that are not as important with health, we tend to know, 0.01%, right? But on average, 1% of all these little squares, we know whether they cause a health problem in the body if you have that specific mutation. Now, what it means is in the white squares, right? If you have a mutation in one of these white squares, that means that that mutation is going to cause a loss of function in your body, and you're probably going to get that disease. Now, if you have a mutation in one of these blue squares, it means the gene is still going to function properly, and even though you have a mutation in one of those blue squares, it means, well, you're probably still going to be fine. You never even know you had a mutation, right? Now, if you have a mutation in one of these light blue squares, what that means is it's probably going to depend on your lifestyle choices, whether or not that mutation actually turns into a disease or not. Right? And so this map that you're looking at has never been seen before because most often, if somebody maps out all the data that the whole world knows about that gene, most of these squares are going to be gray, right? Because we don't know what that mutation does. So we put a gray there to represent we don't know, instead of a blue to a light blue or white, or a black, which means what it should be without a mutation, right? It's gray. We don't know, right? And so most of those squares will be gray. And you'll see an example of that in a little bit, right? So this is what it is. So this is how accurate, this is how amazing it is. Now, you'll see right here, it says accuracy, 94 to 100%. Why is it 94? Well, the reason why is because when we compare this data to correlative data means that you have enough people with this mutation who do or don't have the disease, and so we make an assumption that this mutation causes this disease. Well, guess what? When you compare our measured scientific data, which is the gold standard now, which I'll get to later, when you compare our measured scientific data to correlative data, which is, lower down on the scale, you'll see that later. When you compare it, 94% of the time, our data is not the same as the correlative data. Well, guess what? when you compare our data to any other scientific experimental data, it's 100% accurate. Because correlative data, everybody in science knows, is not always accurate. That's why they call it correlative. And so what we've been able to find out is that of all the correlative genetic data that we have on the planet, 94% of the time they're right, which is pretty good, but 6% of the time they're wrong and they don't even know when or why. Right? So that's what it is that we do. Now, one last thing I want to put on the slide is that our average p-value, meaning our average accuracy, the average amount that our data is right, is way better than the 0.05 that most science goes by. It's 0.0201%. But some of our data, and we know which one, some of our data has a p-value of 10 to the power of 65. Now, how many particles are there in the entire universe, right? Every grain of sand, every atom, every neutron, every speck of dust, everything you could think of just even on this planet, let alone the entire solar system, entire universe, and every other solar system and universe in the galaxy, right? Every piece of something, an atom or whatever, right? Every speck of something, that still doesn't add up to 10 to the power of 65. 10 to the power of 65 is more zeros than there are particles in the universe. That's how accurate some of this data is. I just like to say that because I just like to point out that this is not just some new test that maybe will help you a little bit. This is a new test that has been proven scientifically in multiple ways through published papers, through patent pending, through so many different ways that this is going to help you, right? It is going to help your doctor figure out which drug it is that they should or shouldn't prescribe for you, right? So what we know is we know that if any one of these 6,270 amino acids, right, in the tyrosine kinase region of the HER2 gene, right, we know if that mutation is going to lead to cancer in a petri dish or not. Now, we have not proven to the FDA yet whether or not this cancer-causing mutation in a petri dish is going to cause cancer in a human. But let me tell you what, many, many, many other companies who have produced this data one mutation at a time, they have all shown the FDA that their in vitro, their in petri dish studies correlate human beings. Right? So there's no reason why we can see possible that we're not going to be able to prove that eventually to the FDA as well, but we haven't proven it yet. Right? And again, just a reminder, on average, what you're looking at here, only 1% of these squares, right, 20 up and down, right, hundreds, 330 for the TK region of HER2 gene, right, but 1%, that's all that's known, 1%. We know all 6,270 in the region of the HER2 gene that is commonly known to cause HER2 positive breast cancer, all of them. The rest of the world only knows about 600. We know all 6,000. Right now, I told you earlier, right? I was going to show you, right? This is what it looks like when what we don't know is grayed out, right? You got your 1% down here at the bottom of blue, dark blue, light blue, right? And it maybe not always is going to be in the same amino acid sequence, but that's what we know. And all the other squares, you know what? We don't know what they do. Black is normal now, and on average, if you're a human being, which we are if you're watching it, right? Well, maybe not, who knows, right? But anyway, if you're a human being, these little red squares represent average common mutations that people will have. And 99% of them, we don't know what they do, right? So what we can now do, right, since we have more data, we can better predict how this is going to impact your future and disease. Now, again, we have not proven this to the FDA, but what other companies have done multiple times is they've done this exact same type of assay on one mutation, and they do it enough times, and they finally show the FDA, hey, look, this mutation means this disease, and the FDA finally goes, yes, right? That's what they've always done in the past, but so we have to do that yet. We have to prove it to the FDA, but there's no reason why we don't know that's not going to happen, meaning that, guess what? If your mutation is in one of these little dark blue squares, guess what? That means the function is still there, even though that mutation is, and you're probably never going to get that disease. But if your mutation is in one of these little white squares that is white, that means that you're probably going to get that disease. But if your mutation is right here, one of these light blue squares, it probably means that your lifestyle factors are going to be a determining factor on whether or not you get that disease because of your specific mutation. Right? Now, again, This is not what's proven to the FDA for our data, but it is proven with many other companies and many other data sets like this to the FDA. Right? So this is what it is that makes it so different. So what we expect is that as soon as we prove this to the FDA, this will become the new gold standard of whether or not your breast cancer is HER2 positive breast cancer. Right? But now, what we can do now and what we can say now without proving it to the FDA is what everybody else does, is that when we have shown through enough scientific experiments, which is what we've done, that a drug present, right, turns the white square blue, turns the function of the cell back on, which, and if you notice, if you go back and forth between these two, right, what happens is a lot of white squares, thankfully, from these drugs turn blue, meaning that if you have a specific mutation, say over here, in a white square that turned dark blue with the drug present, what that means is this drug is going to help you. Now, this is what people are already doing. This is what most people call precision medicine, right? So if you've got a mutation in a white square that turns blue with the drug present, that means that you are now sensitive to that drug, right? Doesn't mean the drug will work, but it means you're sensitive to it. And odds are, if the drug actually binds, it's very likely to work. That's just published literature data 80% of the time, right? Now, if you have a mutation, say right here, that if you look at is in a white area that stays white, guess what? That means that you are resistant to that drug and it is not going to work. Now, again, this is not new to the FDA. This is not new to science. This is well known and established in science, right? So if the white stays white, this drug is not going to work for you. Now, because people do experiments on one of these mutations at a time, because people do take drugs with these mutations that cause these diseases multiple times, through correlative and experimental data, we've actually found 3 mutations right here, V842I, L755P, and L755S. We've actually found through correlative experiments and some experiments, 3 mutations that we know that if you take the lapatinib drug, will not work for you. You are resistant. Now, if that means if you have HER2 positive cancer, your doctor should be prescribing a genetic test to see if you have a mutation in one of those locations. And if so, they should not be prescribing lapatinib. Okay? And a lot of doctors do that. Not all of them. Don't ask me why, but they don't. Right? And 38% of the time, if you have HER2 positive cancer, 27% of the time, up here on the right, 27% of the time, one of those 3 mutations will occur in your body if you have HER2 positive breast cancer. So that means 27% of the time of those 3 mutations, lapatinib will not work for you. And if your doctor's not finding out if that's you before they prescribe the drug, I don't know. To me, that seems common sense. But what we found is we found 247 new mutations that cause resistance to the lapatinib drug. Now, we found about the same amount for neratinib and tucatinib, but this is just one example right now. Because these 247 mutations here are less commonly occurring in breast cancer patients, that means that only 11% of the time will a breast cancer patient have one of these 247 mutations. But what that means is since we now know every single one, all 6,270 of those 330 amino acid possible mutation locations with the 19 possible mutations, right? Because we now know every single one of them, we now know that 38% of all patients with HER2 positive breast cancer are going to be resistant to lapatinib. That's 40% almost, right? That's, I'm going to call it close to half, right? Not quite, right? But as one example, right? That means that if you're not taking a genetic test for HER2 positive breast cancer to find out which mutations you have, to find out if the known mutations cause it, that's a huge problem. Now, these 247, no one else in the world knows who they are but us, because we did that experiment to figure them out, right? So that's why you come to us, you take our test to find out whether or not your known mutations were actually going to cause resistance to lapatinib, neratinib, and tucatinib. But now, if you do not have resistance to the drug, for the first time in history, and this is the very first slide I started out on, right? For the very first time in history, we know, oh, you can't see it because of my picture there, but 62% of the time, right? People, that means that they are susceptible. That means they are sensitive. That means that drug is going to bind. And if that drug binds, it's much more likely to work than if that drug is not binding. That's what resistance means. right? So that's what it is that we do. That's why this test is the first of its kind, the only kind for any drug, any disease on the planet to this date. Right? That's why every single person on the planet who has HER2 positive cancer should be coming to us to get this test done. All right, because it will tell you of the three most common drugs prescribed 90% of the time for HER2 positive cancer, whether or not you are sensitive or resistant to the drug. And that is great information for your doctor to have for them to decide which drug you should or shouldn't take. All right, that's what it is that we do that no one else on the planet does. And what that means is this is just a fancy picture for now. We have all these people, right? Some people are resistant to drug one. Some people are resistant to drug two. Some people are resistant to drug three. But nobody on the planet really knows all of those people. Yeah, sometimes we know some of them, right? But what that means is all these people come in, we can do a test, and now we can tell, hey, these people here, right, they can take drug one. These people here can take drug two. These people here can take drug three because it's going to have the best chance of it working because you're not resistant to it. You're sensitive, right? So we have HER2 done with the three most common drugs. We're going to be start working on EGFR and the 11 most common drugs for those. Hopefully have those in the year. And just another way, I said I was going to talk about this earlier. So the American College of Medical Genetics, right, has created levels of scientific evidence. And the gold standard is what you see over, excuse me, over here on the left, right? Level A evidence is FDA approved therapies, professional guidelines, right? Stuff that's been thoroughly proven, right? Level B is well-powered studies with consensus from experts in the field. Well, guess what? This GIGA assay is a level B, right? It's well-powered studies with consensus from experts in the field that when you measure a genetic mutation and its functional effect in an experiment, and you do it enough times, it's well consensus that this provides very accurate data on what it is that the functional effect of that mutation is. That's what the GIGA assay is. Right? So multiple different ways, multiple different times, we're proving people over and over again, right, that this is it, right? We got a published journal in PubMed. We got 3 other published papers as well. We have patents and patents pending. We also have a NIH grant. So NIH grant has looked at all of our data. NIH has looked at all of our data and said, yeah, we believe this works as well. So we're going to give you money to do more of it. Right? So multiple, just so many different ways that this is proven. So it's not just like, oh, we're just some fly-by-night company. Hey, come buy our test, right? We are actually in the scientific community doing things and proving and showing people to everybody from NIH all the way down to published papers, down to the patent office, over and over again, this works. And very soon we're going to have that level A gold study FDA approval showing that this is the new gold standard for whether or not you even have HER2 positive cancer. But so for right now, what we can do is we can compare your mutations against our database to tell you whether or not you are sensitive or resistant to drugs for HER2 positive cancer. So you have HER2 positive cancer? Do you know someone who has HER2 positive cancer? Right? Are you getting the test to find out if you have HER2 positive cancer? You should get our test. Right? TrueGeneDiagnostic.com/order. Right? We'll send you the test kit to you or your doctor. Right? The doctor's going to put you're going to have to bring it into your doctor. If we don't send it to your doctor, they're going to have to put some of your biopsy tissue that they took from your cancer into this test kit of ours. We're going to send it to our partner lab. We're going to get it sequenced and find out which mutations you have in your actual cancer tissue. And then we're going to send you and your doctor a report that tells you, based on your specific mutations, which drugs, if any, you are sensitive or resistant to. And with that information, your doctor can make great informed decisions about what it is they're going to do for your future care. Right? So everybody on the planet, if you have HER2 positive cancer, you know someone who does, they need to take this test. Right? It is going to potentially tell them or save them 6 months out of their life from taking a drug that wasn't going to work anyway because we now know they're resistant and it won't work. Right? So there's all of our contact information. If you have any questions, comments, email me, right? Text me. You can call me, but I probably won't answer. But email and text, I respond to those, right? It's still at the point in this company where I still am responding to people who have questions about this. But at the end of the day, order the test, get this done, and show your doctor the results and show your doctor what it does. And your doctor's going to go, oh my gosh, you're right. We need to get this test. It is amazing. Right? So Thanks for listening. Share this with your family. Share this with your friends. Share this with your support group. Share this with anybody who you think might be HER2 positive cancer so they can decide whether or not this is for them. Again, right now, that's the only one we unfortunately have is for HER2 positive breast cancer, but hopefully in the next couple of years, we'll have lots and lots more types of cancers and lots more drugs added as an available test that patients can actually take. So again, thanks for your time. Thanks for listening. Share this with people in your life and go and order that test now online. Thanks and make your day great.